Okay, today we're going to be looking at what I call comparative surface area and volume. Okay, a bit of review. Continues to use the information on surface area and volume that we've been using, just looking at it from a slightly different viewpoint. Okay. Now, comparative surface area and volume deals with situations where one solid of some kind is becoming part of another, and there's I kind of left that description very a little bit vague because there's a lot of different ways that this can be interpreted. And we're not talking about when we say becoming part of another solid, one solid becoming part of another one. We're not saying like with composite solids where we're gluing two of them together or cutting one out of the other. So it's not like composite solids on that aspect. This is more of like the surface area of one figure kind of being taken apart and then wrapped around a different type of figure in order to see will it cover or will it not, or how many of these figures would you need to cover this other figure, or in the idea of volume, containers that actually have some type of volume in them, some liquid or some type of substance, and then one container is being emptied into another container. Again, will one of them fit inside of the other? Yes or no? You know, how many will it take to fill it? Stuff like that. So that's what comparative really means in this situation. So I've got a few examples put together. So let's see if we can figure these out. For example, if cylinder A is being filled with cylinder B's, okay, which is to say that there's something inside of them. Okay, that cylinder B has something in it, or maybe it's being filled up and then it's going to be dumped into cylinder A. The question is, how many cylinder B's will it take in order to fill cylinder A up? Okay. Okay. Now, what kind of a question is this? Is this volume? Is this surface area? What do you think? Think it's area? I think it's volume. Okay, if we're pouring one container into another, okay, well, we're basically talking about the stuff that it takes to fill something, right? Technical definition for volume, the amount of stuff required to fill something. Okay, so we're filling things. We're filling one up and dumping it into another one to fill the other one up. So that's a volume question. Okay, so when it comes down to it, when we go to select formulas, we'll definitely want to pick formulas that deal with volume. Okay, so going to the formula chart, okay, we would say, all right, I need to know what is the formula for the volume of a cylinder. Well, the formula for the volume of the cylinder is big B little h. What we really need to be able to do, if there is a catch to problems like these, is to write one equation that tells us how are these two figures related to each other for this kind of a question. Okay, well, the question asks how many cylinder B's will it take to make one cylinder A? Okay, so this information that's going on with volume on cylinder A, big B little h, we only need that one time, right? Okay, because we're trying to create one cylinder A. On cylinder B's case, okay, in this particular instance, we don't know how many cylinder B's it's going to take. So what we're going to have to do is we're going to have to write an equation that makes cylinder A somehow equal cylinder B. But since we don't know how many cylinder B's it's going to take, we're going to have to introduce a variable into that equation. And the equation can be written, when you think about it, really very simply. Big B little h from cylinder 1 will equal, we don't know how many, but big B little h's from cylinder B. Okay, so I just kind of threw a question mark in there because it's a variable. Okay, it's a variable. We don't know. And I didn't want to pick a particular variable and put it in there because we've already got a whole bunch of variables running around with the surface area and volume formulas that we're going to be using. But you could pick anything. I just put a question mark in there. Okay. The next thing I did was I converted the big B's to the actual area formulas. Okay. Big B is the area of the base. Well, in a cylinder's case, that's a circle, pi r squared. Okay. So I changed big B to pi r squared in each case, and now all we really have to do is fill in the values that we do know. Obviously, pi is pi. What is the radius from cylinder A? Ooh, that's, yeah, 9. That's not a difficult question. 9. Okay, so we'll plug in 9 for R on the left-hand side, and H from cylinder A, 30. Easy, plug it in. The question mark is unknown. That's what the problem is asking us. How many of those cylinder B's will it take? Okay, so that's going to remain a variable. Pi is obviously pi. And the radius from cylinder B, going to be 4, and the height from cylinder B, 12. There we go. So we're just plugging in numbers. And you really ought to be home free, at this point. We'd go to our calculator and figure out what these values are. We've got pi times 81 times 30 on the left-hand side. We've got pi times 16 times 12 on the right-hand side, and we're going to get numbers for those, and these happen to be the particular number, 7,634.07 equals, we don't know how many 603.19s, but we're solving for this question mark, this variable. So there's only one other thing to do. Got to get the question mark by itself, which means this 603.19 does not need to be there. How do you move that to the other side? Divide it, right? This is question mark times 603.19. We'll divide both sides by 603.19, and the question mark is 12.66. Okay. Well, so the question now, here's the thing. Okay, these questions you kind of got to really think about the answer sometimes. Okay, we've got 12.66. That may very well be an answer choice, but it's entirely possible that the answer choices that you see might be whole numbers. Okay, that maybe 12 is an answer and 13 is an answer, but 12.66 is not an answer. So we kind of have to figure out, okay, would I want to round it down to 12 in this case, or would I want to round it up to 13 in this case? And is it a matter of, when it comes to rounding, am I just looking at that 0.6 and saying, well, 6 is bigger than 5, so that means I automatically round up? Okay, and the answer is it depends on the question. You really need to read the question again and find out, commonsensically, what direction does it have to round? The question says, if cylinder A is being filled with cylinder B's, how many B's will it take? Well, if we have 12 cylinder B's, let's say they fill it up 12 times, dump it into cylinder A 12 times. Did cylinder A get all the way filled up if we stop at 12 fillings? No, it didn't, because there's still that extra 2/3, that 0.66. Okay, so in this case, we would have to round it up because cylinder A would not get filled if we stopped with 12 cylinder B's. So in this case, the answer would be you would require 13 cylinder B's. But again, that didn't really have anything to do with it just being, 12.6, 0.6 means round up. It's not that at all. Okay, because the question might have just as easily said, how many times can you completely put cylinder B into cylinder A? In that case, what would have been the answer? It would have been 12. How many times can you completely put it in there? We'd have been able to get the 12th filling in there, but we wouldn't have been able to get the 13th in there. So we would have had to say, how many times can you completely get it in there? You can only completely get it in there 12 times. So you have to round according to really what the question is asking. But in this case, we needed to round up because stopping at 12 fillings would not have filled cylinder A all the way up. We needed that 13th to get it done. Okay, let's look at another one. This one says a rectangular prism is to be covered with square cloths. How many of the cloths will be needed to cover the prism? Okay, once again, they did not come out and use the word volume or come out and use the word surface area, so we have to correctly identify what kind of a question it is. That way we can make sure we're using the right types of formulas. So what is this one? Is this one another volume question? No. This one's going to be surface area. Okay, they didn't say surface area, but they did say cover. Okay, cover. If you remember our technical definition, surface area is the amount of stuff required to cover a three-dimensional object. Okay. So in this case, we're going to be doing surface area. So what we really need to know is how much surface area is there in the rectangular prism, and then how much area will each of those little squares cover up, so we can figure out how many are needed. Okay. So to put that in the same type of terms, we've got surface area equals, we need to know how many areas. Okay, so again, I just use the little question mark there. You can use any variable you want, or you can use the question mark, whatever. Okay, so we're going to solve surface area on the left. We're going to solve area on the right in order to figure out how many of those areas are needed. How do you find the surface area of a rectangular prism? There's a couple of different ways. The formula chart does provide us with a formula for surface area of a prism. Okay, but you also remember the way we kind of started off doing surface area when it came down to prisms. A lot of times it's just as easy to unfold the figure and look at the net. Okay, and a rectangular prism is really very, very easy. Rectangular prism is built out of three different rectangles. Front and back are going to be the same, top and bottom are going to be the same, left and right are going to be the same. So all we really need to do is just kind of eyeball the figure, or eyeball our prism here, and figure out what those measurements are going to be. Okay, over there on the right-hand side, okay, very easily, we're going to figure out the area of that little square cloth. And we know it's square because the problem called it square. Okay, well, let's pick out some sides here. Surface area. Okay, I've got 2 times each of the different sides, because again, front and back are going to be the same, left and right are going to be the same, top and bottom are going to be the same. What are the measurements that we have available to us? Pick one of the sides, any of the sides. What are the dimensions of any side for the rectangular prism? 17 by what? 11? Okay, there you go. There's one of your sides, 17 by 11, and we've got 2 of those things. Okay, what's another side that we've got? 9 and what? 9 and 17? Sure, there's a different side that we've got there, and there's going to be 2 of those. What's the remaining combination that we haven't seen yet? 9 and 11. There you go. Okay. How about the area of our square? How do you find the area of a square over there? Length times width, which in a square's case is the same value twice, right? So we get 7 squared. Oh, let's see if we can do these. I don't have my calculator going on my computer, so let me see if I can get this right. 17 times 11 is 187, and if you double that, that should be 374. If anybody has a calculator, double check me on that. 2 times 9 times 17. Be 18 by 17, 289, 306, I believe, on that one. Hopefully I'm not making a mistake there. And the last one, 9 times 11 is 99, and if you double that, you get 198. Okay. Now, assuming I haven't goofed anything up, we ought to be able to add up these 3 area calculations that we just got, and that would give us a total surface area. That's 18, 17, and 8. Okay, so it looks like 878, whatever it is, centimeters squared. And we've got 49 on the area of that guy. Okay, so kind of continuing to plug this into the formula that we got 878 equals how many 49s? Okay, this is going to get ugly here without a calculator, so I guess I might as well grab one, because here we're going to have to divide by 49 to get the 49 away from that question mark. And I'm going to take 878 and divide it by 49. Yeah, and I got that as well, 17.8. .92 is what my calculator just spit out to me. Okay. Now let's see. We've got a .92. Our instincts would be to round that to 18 if we had whole numbers. But let's double check the question. How many of these claws would be needed to cover the prism? Okay, well, it's saying we need nearly 18 claws. So if we pick 17 as an answer, is that going to cover the prism? No, we're going to have .92 of that 49 cubic centimeters there will still be uncovered. So we are going to need the 18th cloth in order to get that. So that's going to be our answer. It'll take 18 squares. So 17.92 would be the exact answer, assuming I haven't messed up anything in those numbers there. So 17.92 would be the perfect answer. But if whole number answers are all that's provided for us, we will need the 18th cloth. Otherwise, part of the prism will still be exposed. This is basically the way it works, so it's just kind of the same thing over and over again. All they can really do is change the shapes. Okay, let's look at one more. A cone is leaking from the vertex. In order to save the fluid inside of it, hemispheres are used to catch the drips. How many hemispheres will be filled? Okay. Hopefully we're able to identify that this is a volume question. Okay, since we're talking about water being inside of these things, that is stuff required to fill. A basic description of the problem at hand would be the cone equals how many hemispheres. Then we would go to our formula charts and say, okay, I'm going to need these formulas here. Okay, well, volume of a cone, 1/3 big B little h. Okay, and that will equal how many hemispheres. Okay, well, hemispheres are, or total spheres are 4/3 pi r cubed. But to be a hemisphere, we are only interested in half that amount. All right, you just have to plug in your information here. 1/3 right, times big B. All right, well, big B of a cone is a circle. So that's a 1/3 pi times the radius squared. What's the radius of our cone? Going to be an 8. Right, times the height of the cone. All right. Yeah, so we gave 17 on the lateral height. Okay, so we need to know what's going on with that height inside of there. Okay, so we got an 8 on the radius, 17 on the lateral height, and an unknown overall height. Well, don't recognize these numbers. Well, I recognize them. I don't think y'all probably recognize them. Let's see if we can figure out what's going on with the height here. We've got 8 squared plus the height squared equals 17 squared. 8 squared is 64. 17 squared is 289. Subtract 64 over to the other side, you will end up with 225. We're going to take the square root of both sides. Does anybody know offhand what the square root of 225 is? It is exactly 15. Okay, once again, what's this vocabulary called where all three sides of a right triangle are whole numbers? Pythagorean triple, exactly. Okay, so, but we have a height of 15 on our cone. Okay, and that's a lesser known Pythagorean triple. As a matter of fact, I think that's one of the ones that even a bunch of math teachers don't even have that one memorized. You don't see it very often. Okay, but anyway, the question mark is the goal of the problem here. What else do we have? We got 1/2. We've got 4/3. We've got pi. And we need a radius for our hemisphere. What's the radius of the hemisphere going to be? Yeah, just one, right? 2 feet across on the diameter. So we have a radius of 1 foot this time. And we got a bunch of decimal points here. Okay, got my calculator going here finally. Let's see what we have. We got 1/3 on the left side, pi. We got 64 on the 8 squared and 15 on the height. Now obviously I've hit a wrong button. Look at all this junk I've got showing up in the exponent. So I'm just going to clear this back out. Okay, see if I can't write this down a little better. 1/3 pi. Not real sure what it's doing on that exponent. I'm just going to start over. 1/3 pi. Did it again. Okay, there we go. Times 64 times 15. And it did not like that as well. It's complaining about that exponent that it's trying to bring in there. See if I can delete it. There we go. Okay, so we got 1005.31 in the ballpark thereof equals how many of that hemisphere? No idea. Okay. We want 1/2 of, my board is getting worse and worse on its calibrations, 4/3 pi. And you've got 1 times 1 times 1. 1 cubed is, of course, 1. So you don't even have to put that in, but you can put it if it makes you feel better. Okay. And you got 2.09, something in the ballpark. 2.09. Okay. Obviously, it's going to take quite a few of these hemispheres if each one only has 2.09. But let's see how many of them it'll actually take. 2.09. So we've got 1005.309649 divided by that answer that we just came up with. And let's see what we've got. Wow, that's strange. I made up this problem on the fly earlier today, and it came out almost exactly 480. So there's our answer, I believe. How many hemispheres will be filled? Well, 479.9999999. It was 480 hemispheres. That's basically the way it works. Again, all they can do is they can change from surface area to volume. They can change shapes. I can see where questions would be worded in the sense that, hey, you've got this one shape and that one shape. What percentage would be covered, or something like that. But in the end, all they can do is just change the way the question is asked, change the type of questions that are being asked, change the shapes in the questions, and so on. And that is it.